Hey everyone, so I just wanted to make a note about these proline rich motifs. So notice that uh, unlike all the different recognition sites that we discussed earlier on, these proline rich motifs, or these prolines, don't have to be phosphorylated in order for these domains to recognize them. Okay, so all these other domains that we talked about previously, they're all phosphorylated: tyrosine, phosphorylated serine, threonine, and so on, right? But this proline-rich motifs are very stable by themselves, and they don't need any modifications to stabilize them. So anytime there's a polypeptide with lots of prolines together, any of these domains will recognize that and bind to it. So SH3, WW, and EVH1. So that finishes our families of domains, and now we'll talk about modular organization. Modular organization, and this is pretty much memory work. So like I said before, the proteins that act that have a part in cellular signaling events, or just cellular events in general, they are organized in modules. So let's look at some examples. Now this could be drawn in a table form too, but I'm just gonna go like this. So adapter proteins, and we'll talk about what adapter proteins are in a later video, but an example of an adapter protein is GRAB2, and this is basically made up of 3 domains: SH3, SH2, and then SH3, and that's it. That is its modular organization. So just a quick review. SH3 domains recognize what? Proline rich motifs, right? So that's for SH3. And SH2, they recognize phosphotyrosine. Let's just quickly check it. Yep, so SH3 recognizes proline rich motifs. So that is the modular organization of your GRAB protein. And yes, this needs to be memorized, unfortunately. The next one is your kinases. So this is like a general structure. An example we could use is SRC kinase. Now this is exactly like the adapter protein, except for one change. So you start with an SH3, then you have an SH2, and then instead of an SH3 here, you have a Y kinase domain. Obviously, right? Because if you don't have a kinase domain, how is it going to do its function? So this probably is the catalytic domain. Okay? So the kinase basically means adding something, and in the case of a protein kinase, it would be adding phosphate groups, right? So that is this domain that does that function. Next example, just going to use a different color, is phosphatase, so just the opposite of a kinase. Phosphatase, and we'll use the example SHIP, I think. Yep. SHP2. Now this looks a little bit different. It has an SH2 domain, then it has another SH2 domain, and then it has a phosphatase domain. So it needs to have these domains, right? If it doesn't have the phosphatase domain, then it cannot do its function of phosphatize or dephosphorylating different proteins. So that is the structure of a phosphatase, like a general modular organization of a. This is how they're usually set up, and then specifically like SHIP2 protein is set up this way. Let's do another example. RAS signaling. This is going to be very, very important. RAS signaling. Let's look at its domain structure. So RAS signaling has an SH2 domain, then it has an SH3 domain, then it has an SH2 domain again, then it has a pH domain, and we will get to pH domains a little later, then it has a C2 domain, and then it has the RAS GAP, and this is the example that I'm using here is of RAS GAP, so that explains it. So SH2, SH3, SH2, pH, C2, and then RAS gap. There's 2 more examples, and we'll just continue those in the next video.